So welcome everybody to our last session of this event. It's an afternoon session. I hope that you cast your votes because we have already the results, right? Will be announced at the end of the conference, all right? Thank you all for participating and for voting. It was very important. I have another announcement that I forgot, but I will remember somewhere. We have now two presentations, and afterwards we have a tribute session, right? In honor of Poti, that is coming. He's not here, but he's coming. And then we'll have the award, and then the last coffee break and the farewell, all right? So our afternoon will be a little bit shorter than yesterday, right? Okay, it's a pleasure to introduce you Professor Jonathan Evans. Professor Jonathan Evans from University of Bath in UK. And he has been also a long-time collaborator here with Poti and Cássio and Irineu, and with some projects. Right now, the Sprint project is going on, right? So it's a very, very fruitful collaboration with Professor Evans. He's going to talk about extrudate swell singularity for PTT and Giesecke's viscoelastic fluids. Jonathan, thank you. Thank you for coming. Thank you for accepting the invitation.
Well, let me start by saying thank you very much, Fabrizio, for the invitation, and thank you for organizing such a nice workshop. I was at Poti's 62nd celebration, I think, a few years ago. So this is which Cássio was in Iguazu. So I'm here, I'm very pleased to be at the 70th, and I look forward to being at the 75th as well. Okay, as Fabrizio said, I've been collaborating for many years with several people, and Cássio, Irineu, as well as Poti, of course. Also, a few years ago, Murillo, sadly no longer with us, but Sean McKee reminded me that we actually had a joint paper, and so both Sean and myself were co-authors, although we never really interacted on the problem, talked to each other. Okay, so today I'm going to talk about a problem. It's a benchmark problem in viscoelastic fluids. So it's the common name, or the current name, is extruded swell, and the old name was called dye swell. And the thing is, for viscoelastic fluids, you have this swelling when the fluid exits a channel and emerges at a jet. And this swelling can be 2 to 3 times greater than in the Newtonian case. There are many applications of this, particularly to extrusion products, right? Pipes and tubing, molding products, and also coating of wires and cables, etc. The reason you would like an accurate simulation of the problem that would allow you to produce more, vary the parameters and investigate material and flow changes for different products. And the simulation should be less costlier, both time and money, than doing things experimentally, for example. Unfortunately, this problem has a lot of difficulties for numerical simulation. And one of the difficulties is associated with the change in boundary condition that you get from the channel to the emerging jet. And that change in boundary condition induces a singularity in the stress field. And this singularity is extremely problematic numerically. So the goal, and really the big question, is what is the singularity and what is its influence on the emerging jet surface? So I'm going to look at 3 viscoelastic fluids: Pantheon Tanner, Giesecke, Oldroyd B. And we're going to do the analysis in planar flow, and the asymptotics are presenter for the steady problem. To orientate it, we've got flow coming in from the right-hand side. It's a fully developed precise flow, exits the channel, and then in the jet eventually transitions to full plug flow. Okay, so for the asymptotics, we're going to look locally to that, to the die lip. So we've got the solid boundary for the channel, and then we got the emerging free surface. And I'll take local coordinates centered at that point, and we'll have polar coordinates. Most of the things are present in terms of polar coordinates, the radial distance and theta. Theta naught is the upstream wall, the channel wall, and theta alpha is the downstream surface. And technically, theta equals alpha is the tangent, gives the tangent line of the attachment of the free surface to the die, to the channel. So we're going to solve usual equations: conservation of mass, conservation of momentum. It's slow flow, no inertia terms. And the stress is going to have 2 contributions. One is from the solvent part and the other from the viscoelastic polymer. So it's a Newtonian constitutive relation for the solvent part, and it's a constitutive equation of this form for the viscoelastic part. So here we're going to have the linear stress term. We've got this upper convected derivative of stress, and that's the memory term. We have quadratic stress terms. So the upper one corresponds to the Pantheon Tanner model, and the lower one to the Giesecke model. And you've got the rate of strain on the right-hand side. So as usual, rate of strain, symmetric part of the velocity gradient. And this upper convected derivative is composed of 3 terms. So the advection of the stress, that's the first term. And then these 2 other terms involving the products of the velocity gradient and the stress. These arise from the representation of the stress as in the contravariant form. So it's the change, it's the motion of the basis vectors when you do a contravariant representation for the stress tensor. If you do a covariant representation, then those terms change sign and you get positive. But here, the upper convected derivative is far more realistic. And in the problem, there are 3 parameters. So the Weissenberg number controls the effect of the upper convected derivative. Without loss of generality, because we're doing the problem locally, we can scale it out. So we'll set it to 1, but it also holds for any Weissenberg number, particularly large Weissenberg numbers. Beta is the solvent viscosity. So this varies between 0 and 1. When its value is 1, we lose the viscoelastic stress. We have pure solvent. And when beta is 0, the other extreme, we lose the solvent and we have pure viscoelastic stress. And then there's a third parameter, I've called a kappa. This controls the influence of the quadratic stress terms, basically, for the two models. Okay, so let's, I'll outline what exactly the solution strategy is. We have boundary conditions associated with these governing equations. So on the solid surface, we have the velocity is 0, no slip, no flow through it. And on the separation, we're going to impose no normal flow and the 0 shear stress. Now, technically, this is a free boundary problem. So we need to determine the free surface as well as part of the problem. So this separation line, the tangent line, if you like, it's a linearization of the free surface. Now, if we impose, there's a third condition on the free surface, and that is the balance of the normal stress. And if you impose that on the separation line, then it's over-determined. And this was a result that was known back in 1952 by D.H. Michael for a viscous fluid. So separating from a straight line, a viscous fluid, if you impose the normal stress condition along with the other conditions, it can only emerge in the flat case. In other words, it can't be supported at an angle. So what we're going to do is solve the equations in the sector, right? Theta is naught to theta is alpha. Alpha, then, we're going to call the separation angle. And it's going to be a parameter of the problem. So we're going to do it for all alpha of interest. And what determines alpha? Well, it's actually the full flow equations in the channel themselves. They will pick a specific alpha at any given flow moment. So we'll actually look at this problem with the 0 shear stress on the free surface. And then once we solve that problem, we can use the normal stress condition to determine the free surface itself. So in other words, the influence of the surface tension term is to produce the curvature in the free surface as it leaves the channel. Okay, it's worth summarizing the Newtonian result because for the PTT and Giesecke's fluids, this is the relevant flow field. And we'll see why in a minute. So Stokes flow for a Newtonian fluid, there is well-known separable solutions. And since we're in planar flow, we have a stream function. So we're solving the biharmonic equation with the given boundary conditions. These separable solutions, it's a power law in the radial distance with a suitable function of the angle. And it's an eigenvalue problem for the exponent. And there's a transcendental equation to determine that exponent. And this has been known for a very long time from the early work of Dean and Montagnon, and then Moffat did it in a lot more detail back in '64. From our point of view, we noticed that this separation angle alpha, once you get above 132 degrees, that exponent goes below 1. And going below 1 means that it induces a singularity in the velocity gradient. So in other words, the region where of interest for the extruded swell is between a separation angle of between 180, and 270, right? That's the range we're interested in. So our velocity gradients are going to be very singular when you've got to differentiate this twice. So these exponents go negative for it, for the velocity field and the velocity gradient. So that in turn induces a singularity in the viscoelastic stress as well. Okay, a summary of the asymptotic structure. It's a three-region structure. So we have an outer region where basically we have Stokes flow for the velocity field, and your constitutive equation for the elastic stress is this upper convective derivative that dominates. And then as you go to the two surfaces, although the velocity field satisfies the boundary conditions, the elastic stress does not. And as a result, then, you get stress boundary layers. And if you notice, we pulled back the certain terms in this constitutive equation. So, for example, at the solid surface, we pulled back the quadratic stress term and the rate of strain term. Whereas at the slip, the free surface, we only pull back the quadratic stress. So these boundary layers are very different, and they have different solutions as well. The details for both the PTT and the Giesecke were published, and this work was done with another Evans, who was a PhD student of mine. It's probably worth seeing it geometrically. So these are fixed streamlines. So with the boundary layer thicknesses plotted, right, from the results that we get. And I'm going to show you the results in a minute. So you can see that you're within the upstream boundary layer, you emerge into this outer region, and then you get into the boundary layer at the slip surface. And the dotted lines are the PTT boundary layer thicknesses, and the ones below them are the Giesecke boundary layer thicknesses. So the boundary layer for Giesecke is a lot narrower than you get for PTT, for example. Okay, so let's have a look at the structure of the outer solution. So as you approach the singularity, then we have that for these two models, the viscoelastic stress is subdominant to the solvent stress. So in other words, the solvent stress dominates. A priori, you don't know that. So there are only three cases. So either one dominates the other, or they're comparable. In two of the cases, you run into contradictions very easily. So for this case, for the PTT and Giesecke models, it's the polymer stress that is negligible. And that allows us to neglect it in the momentum equation, and so we get to Stokes flow. And then we know what the velocity field looks like. And we have our velocity gradients with this singularity. Lambda naught is the first eigenvalue. In the constitutive equation, the viscoelastic constitutive equation, the upper convective term dominates. All the other terms are smaller. And there's an exact solution to that equation. And it's quadratic in the velocity field, right? That's the dyadic product of V with itself. And there's an arbitrary function. And this arbitrary function is a function of the stream function, right? So in other words, it's constant along streamlines. If we take a power law form where we need to determine the exponent, we can generate separable solutions, similarity solutions for the problem, right? And once you do the analysis, you can determine the actual singularities. So for PTT, it's this power, and for Giesecke's, it's this power. And you can check for each alpha, there's a corresponding lambda naught, and you can check that these are both subdominant to the solvent stress. So our criteria is validated, it holds, basically. All right, to give you an idea how you determine these exponents, right, for this stretching solution and also for the boundary layer thicknesses, etc. I'll show you for the boundary layer at the upstream wall, right, at the solid wall. So here, basically, your velocity field is going to be quadratic. The stream function is going to be quadratic in the normal coordinate. And it's the shear rate that dominates. And I'll call the shear rate gamma dot. The elongation rate, E dot, is small. Now, in this region at the wall, shearing then dominates. And so for PTT and Giesecke's, we know the stress behavior in a shear flow. So we have these powers of the shear rate. And you only then have to ask the question, well, these terms have to grow. Well, the elongation rate term has to grow as you emerge out into the outer solution where the full terms of the upper convected derivative now balance. And so that's enough to say, okay, you put these two, the sizes of these two terms together, and that determines for you the thickness of the boundary layer. In other words, where you transition from the shearing flow to this outer stretching behavior. And if you use the stretching behavior as well, then you can determine that unknown index, and you can determine the singularity as a result. So it's that upstream wall that determines everything. Once you've got all these behaviors, you can then go and look at what happens at the downstream surface. And here it's elongational flow because of the slip behavior that dominates, and the shear rate is very small. So what we know that we're coming from a region where these terms dominate. So what and the stress is growing in that region. So the question is, what happens to arrest that stress? And what that stress is arrested by the quadratic stress term. And if we do that, then we can determine the boundary layer thickness, and we can determine the behavior within the boundary layer at that slip region. And I'll show you a picture in a minute showing this transition of the stress between the three regions. Now, it doesn't really matter whether you do PTT or Giesecke's, the behavior is the same, but what does change is if you go to the Oldroyd B model. So the Oldroyd B model doesn't have the quadratic stress term, so we lose that term. So in other words, there's nothing now, this term is very small, there's nothing to arrest the growth of our upper convected derivative. And that has a significant consequence. And I'll tell you what that is after the next picture, I guess. So all I'm going to show now are the constitutive equations, right? These are in polar coordinates, integrated along the theoretical streamline from our Newtonian solution. Okay. So this is it. It's on a streamline going close to the singularity. So we integrate the full equations and we'll compare them to the solution for the different regions. So in yellow is the solution to the upstream boundary layer. And we can see that we start losing it at a certain small radial distance where we transition to the stretching behavior of the outer solution. That goes through a minimum. And as we're approaching the downstream wall, this stress grows. And once you get close enough to that downstream slip region, the downstream, that quadratic stress term in PTT and Giesecke's takes over and brings the stress back down. So you no longer have unlimited stress growth. So what happens with Oldroyd B is that you don't have this blue curve as you approach the slip region. So the stress just keeps on growing. And so what that means is that for the Oldroyd B model, you get infinite stress at the lower surface. So it's not only a stress singularity at a point, at the separation point, it's now infinite stress along the whole of the slip surface. So in other words, Oldroyd B is ill-posed. Just to show you the completion of the analysis. So once you've got the velocity and the stress fields in the sector, right, north to alpha, you can use them in the normal stress balance to determine the shape of the free surface. And its shape is, not surprisingly, influenced by the Newtonian eigenvalue. Okay, so that was the local asymptotics. So next we tried to see if our numerics could capture these, right? So this is, we did simulations using OpenFOAM and using Rio tool. And they've got an implementation of a volume of fluid method. This orientation is now back to front. It's 180 degrees to what I showed you before. So we've got to switch around a little bit because this is their orientation in the Rio tool setup. The minimum spacing on our mesh was about 3 times 10 to the minus 3 in the region around the singularity, the die separation point. We did the simulation in 2 formulations. So the first one is the standard Cartesian formulation. So that's in the fixed basis, I and J. So these are your standard Cartesian components. Now there is another formulation called the natural stress. And that, instead of using the fixed basis vectors, I and J, it uses the velocity field and a vector perpendicular to it to span the stress field. So those components, this was an idea originally introduced by Michael Renardi. And as we'll see, numerically, well, for the asymptotics, it's extremely important. It communicates the correct information from one region to the next, whereas the Cartesian, you've got to do a lot more work. But also, it seems to be very, very beneficial numerically as well. So the analogous components of stress now are lambda, mu, and mu. Right? So just to show you what the equations look like. So these are the constitutive equations for the viscoelastic stress. This is the Cartesian standard, right? This upper convective derivative, highly coupled spatially, right? This is the natural stress formulation. Notice that these are time derivatives, all right? So at steady state, you lose these, and you need to be focusing on these terms. And you notice there's a significant decoupling between the equations at steady state. And that, to me, is one of its significant advantages. Okay, so this is a simulation. It was for the Giesecke's model, Weissenberg 1, beta 0.5, kappa 0.1. And this was the steady state solution. We estimated alpha by fitting a tangent line to the free surface, which was approximately 192 degrees. So we could determine the theoretical eigenvalue for the Newtonian solution, right? And what I'm going to show are the results coming in at an angle of 120 degrees. So this is going in as the radial distance shrinks to 0. So the first plot is the Cartesian formulation, right? So here's your radial log of the radial distance, and this is the log of your stress components, all right? And the bold lines are the theoretical slopes, the asymptotics. And you can see the convergence is very slow and doesn't quite get there, in fact. For the Cartesian, you need a finer mesh again, probably several orders of magnitude more. Let's have a look at the natural stress. This is our natural stress components, lambda, mu, and u against the radial distance. Far faster convergence to the behaviors, right? And in fact, there's a link between the natural stress and the Cartesian, so we can turn these results into the Cartesian equivalent. And this is what the natural stress give us for the Cartesian component. And we can see that we're now starting to get to that theoretical behavior. So the natural stress not only converges faster, it gives you better estimates of the Cartesian stresses, basically. Okay, so everything I've said is for a solvent viscosity. So in other words, that solution construction is only for beta positive. If you put beta to 0, so in other words, polymer melt, no Newtonian contribution, the results no longer hold. So the question is, well, what is the singularity of the solution structure in that case? Don't know. The Oldroyd B, this is what I described here was essentially the Oldroyd B behavior in the Newtonian velocity field, because that was the field appropriate to PTT and Giesecke. So in other words, it was fixing the Newtonian velocity field for Oldroyd B. And the conclusion is there's an infinite stress at the slip surface. Now, the Newtonian velocity field is not the correct velocity field for Oldroyd B. So because the dominant switches around, okay? So in other words, for Oldroyd B, the elastic stress dominates the solvent stress. So the flow field is slightly different. And the flow field is actually a potential flow solution. So the question is, does that change the behavior at the free surface? And the answer is, no, it doesn't. You still get infinite stress. Only the full, right? So in other words, if you let the velocity field be what it should be for Oldroyd B, you're still going to get that same behavior. Although that work is not published, right? Okay, and that's it. So thank you for listening. And Potti, happy birthday, really. And you weren't here at the beginning. I said I'm looking forward to the 75th celebration as well. So thank you.
Retiring. Oh, yeah, in 5 years, yeah. That's true. Questions? I have time for a few questions. Cássio?
Thank you, Jonathan. Nice talk. You summarize everything in a few minutes. How difficult is to extend for DICE this investigation considering the FINI-P or FINI family? Do you have some idea about the mathematical problems and this?
Yeah, I mean, the main thing is we know a lot about PTT, Giesecke, and Oldroyd B, right? So you've got to understand if there are boundary layers and what the structure of the boundary layers are for those models. And that is all work to be done effectively. I suspect the structure is going to be very similar. You're going to have, I can't see it being different from a 3-region structure. It would be surprising. And it would be surprising if it didn't have boundary layers as well, because of its viscometric behavior, basically. So, but the details of it, of course, are going to be more involved. They're slightly more involved equations, right? And we don't know. The nice thing about these models is you're getting power law behavior. And the power law behavior allows you to make analytical progress. For example, if you change the PTT to the exponential PTT, then all this analytical stuff disappears, right? You just don't have tractable, it's far more difficult. So the answer is, I don't know until we do it, basically.
Okay. More questions? Sean?
It may not be a sensible question, but the fact that you get this infinite stress, I mean, if that's unrealistic, does that mean the Oldroyd B is slightly suspect, perhaps, as a model?
Yeah, well, that means it's totally ill-posed. It's an ill-posed model to use. And we've got hints of that, haven't we? Because at certain elongational rates, at finite elongational rates, the Oldroyd B stress goes infinite. And that's in a very simple pulling flow. And so that's effectively what's happening here. So that singularity is allowed to propagate, basically, along the free surface because it's a stretching surface. So in other words, the Oldroyd B stress hits infinity at a point, and somehow, well, it's just, there's nothing to stop it spreading, basically.
That's interesting, thank you.
Yeah, and that also explains why the simulations don't work. Oldroyd B for extruded swell is a lot of problems. You'll see oscillations in the free surface, and this is at small Weissenberg numbers. So they've had all sorts of problems numerically trying to simulate it. And it looks fundamentally, it's because it's ill-posed.
Any more questions? Irineo? No? Okay. Oh, Michael. Yeah, but I have to give the microphone to you.
Thank you very much. So just these, this quantity d extra, the extrusion diameter.
Yeah.
Is that something that's known even before anyone does any numerical simulations, or do you have to do the simulations too? Because I was just wondering whether out of all of this, whether there might be an analytical result that if you knew it before you did the simulations, it would be a good way to check whether the numerics are being done correctly.
No, because the free surface is not necessarily monotonic. So you could do a conservation of mass, so technically, right? But you can get a peak in the free surface and then it shrinks back.
Oh, okay. Well,
so it depends on the flow problem.
Yeah. Okay, thank you.
Yeah.
Okay, let's thanks Jonathan again. Thank you. Right. So the next speaker and the last one. Oh, not the last one. We have an extra speaker.
Okay.
But actually, closing this scientific session, I have the honor to introduce here Cássio Ishii. Cássio is from State University of São Paulo in Presidente Prudente, the best city in the world, right? Presidente Prudente. I was born there, so that. And Cássio did his PhD here with Professor Cuminato under his supervision, and has also collaborated a lot with our group and with Professor Cuminato along all these years. And yeah, it's really a pleasure to have you here, Cássio. Thank you for accepting the invitation and for coming. Please, the floor is yours.
Well, thank you, Fabrício, for introduction. And it's a big pleasure to be here to celebrate this moment with Poti. And I remember, Jonathan, 10 years ago, we celebrate with Yuan and Mario Martinez at the Foz do Iguaçu. Now we are celebrating again. Yeah, good. The title of this talk is Scientific Machine Learning, Frameworks for Viscoelastic Dynamics. This is very particular because usually we can extend for non-Newtonian fluids in general, but for this talk, I just considered viscoelastic one. And after this excellent talk of Jonathan, then the audience observe some equations, some constitutive equations, and then I will use part of the equations just to clarify the idea about viscoelastic dynamics. But if I have time, I hope that I can complete in 30 minutes or maybe 35, 40 minutes. I would like to conclude my talk with different dynamics, not only viscoelastic one, but using moving interface problems. Then let's see. The first, just to remember, some years ago, I was here, and then we developed some codes, in-house codes, to solve complex problems on that time, like jet buckling, and this is the rod climbing, rod dipping. And we investigate different types of viscoelastic models, and also we improve some mathematical models and also numerical strategies to deal with moving interface problems like free surface flows. And then we compare Newtonian and non-Newtonian fluids for different geometry. And part of these works we developed here in São Carlos with the group, the Elicad group. And then we have some memories to now this, after some years, we can just remember this. All right, but today I will talking about a different subject. It's in some sense it's related, and I adopted two nice definitions. The first one was proposed by Quarteroni, Alfio Quarteroni, and then I think it's important to describe, but what is scientific machine learning? Then, according to this paper published last year, Alfio Quarteroni described that this combination of physics-based models and also data-driven strategies. And then you can combine physical laws and mathematical formulations, but you also can, you can also include in some description in terms of the data. And then this is the idea to combine and create this new area, scientific machine learning, okay? But I prefer this last definition, or this definition about a recent comment in terms of what is scientific machine learning, because observe in this definition, we have some details in terms the science problem, constraint, and methodology, and then we can include in this type of knowledge more than just apply a machine learning architecture or just a black box method, okay? And then this is just to have some idea about my talk about scientific machine learning. In terms of non-Newtonian, we have some recent papers, including papers published this year in the last year or 2 years ago, where we can observe the concept or the idea of physics informed. And then this is important to include in when we are constructing methodology in scientific machine learning. It's important to know about the physics behavior, the physics or the laws, or some description in terms of the mathematical formulation. I included here one paper published by Ronnie Thompson, Elias, and also Roberto. Then Roberto worked in this part of this paper. And then it's important just to clarify that we have new development using this concept of scientific machine learning. Okay, this is the part 1 of this talk. I will describe some methodology in terms of viscoelastic benchmarks, and then I just adopted classical benchmarks, classical problems, some classical geometries, just to help us to understand the behavior of these data-driven schemes. Okay, are you talking about not only linear dimensionality reduction, but mainly in terms of nonlinear dimensionality reduction? And then I will take some minutes to describe my idea about physics-informed dimensionality reduction, okay, using the concept of the energy. And also, we include in this talk, we work in some machine learning models in terms of the super resolution using physics-informed autoencoders. Okay, this in terms of geometries, as I said, you adopted classical one like this. We have the cavity flow, we have the cross-lot geometry, and also to capture the influence of the elastic turbulence, you can use this very simple geometry. We define the 4-row mills, and then this is important to capture the information in terms of the stagnation points. In terms of separation in the flow, we have extensional or shear dominated problems, and also when you have the mixed kinematics, and then like, for example, the contraction or including this more related to these different geometry of the contractions. Okay, mathematical models, as I said, we adopted the classical ones, and observing this table, we have the models, the viscoelastic models, and then Jonathan described about the odroid B, the Giesecke, and the linear version of PTT. While here in this table, we can observe the inclusion of these Fini versions or Fini families method, like Fini CR and Fini P. Looking for the mathematical models, you can observe we have the mass and the momentum equation, and also the constitutive equation in a more general form, where C is the conformation tensor. And it's important to highlight this part where C can be decomposed using this tensor B, okay? Because C is a symmetric positive definite matrix, and then we can decompose exactly like this. We have some parameters. If you look for here in the table, we can observe some parameter related to different models, but basically we include the information of the mathematical models in our methodology. Okay, in terms of reduction, we have the high dimensional, we have the data in the high dimensional domain, and then now we needed to apply some of this strategy, okay? The first one is the classical SVD-based decomposition, where we have the PCA, the principal component analysis. This is a linear version of the dimensionality reduction. And in fluids, we call proper orthogonal decomposition, but the POD is the same thing. We have a little difference in terms of numerical construction. In terms of nonlinear version, we have the first one is one extension of the PCA, is the kernel PCA. And more recently, we have this autoencoders strategy where you include a different perspective, but it's considering like a nonlinear dimensionality reduction. just to remember about some linear algebra concept, we have, this is the PCA, where we include in the matrix, or the data matrix, and then you just apply the SVD decomposition. Then this is very simple, it's a classical one, and you can construct the rank according to our interest for the principal components. And then this is the idea of PCA, just to remember. In terms of nonlinear extension, in this case, for PCA, we have this version, this kernel PCA. And then I included in this slide some important concept behind the kernel PCA. The first one is in terms of this data are embedded in a higher dimensional space. We have some mathematical properties to do this, or to conduct this extension in a higher dimensional. But in terms of numerical methodology, we can use the kernel trick, where you just construct based on one eigen decomposition. We can select, and you select the kernel, and then we solve the problem using the eigen decomposition scheme, or some scheme just to approximate the problem in terms of the eigen vector solutions. This is the idea to extend the PCA to kernel PCA. Okay, and then 2 years ago, we published this paper where basically we combine the concept of energy-based kernel embedding. And we have this representation. This is, I will talking about the reconstruction, but basically we have the data, and we included some mathematical description to construct the kernel PCA according to the viscoelastic model, basically. Some ideas about this. The first step is to define the state vector. In this case, Q, we combine the velocity field and also the conformation tensor. After this, we can analyze these terms in terms of the energy. We use the mathematical properties about the reproducing kernel Hilbert space, where in this case we capture this feature map according to this description in terms of the energy. And in this, in particular, we can look for the energy as exactly the kernel function, where the energy in this case for viscoelastic models, we can extend the kinetic part plus, or you add the elastic energy in this part, okay, where you have the Reynolds number, and this is the viscoelastic parameters. Remember, we have beta and Reynolds and Weissenberg number. This is one additional term, but the energy depends on the vector Q, and where in this case tau is just a conversion to the conformation tensor. Okay. This is the theoretical result in terms of different models. And then as I said, if you select the model, you can explain the model, or you can reproduce the model or construct the model according to the kernel function, okay? And then for each model, we have a different kernel function. Then this is the difference in terms when you change the models on this table. And of course, we have simple models like, for example, the Odroid B, but in some sense, we have more complex model like, for example, nonlinear PDT, where we included more terms according to the definition of the kernel function. Basically, then this result help us to define the kernel function according to the description of the energy, okay? Observe that Q2 is this part, and then we select the model, and then you construct this function. Okay, now in terms of benchmarks and the results, the first test, we select this classical transient lead-driven cavity flow. It's important just to include in some dynamics in this flow, and then observe on the lead. We impose one function as a function, time function in this case, and we measure the error or the reconstruction error according to these metrics, and then you can select and according your specific metrics to analyze the reconstruction of the field or just to look for the mechanical energy inside the system. We also included here results for the error in the kernel Hilbert space, where you can use this expression to analyze the influence of the models. Okay. We selected 2 different simulations where you combine the parameters like Reynolds and Weissenberg and beta, and observe that according to, if you compare, we have the simulation using Odroid B, you have the PCA, the linear version, and you have the kernel PCA using that description in terms of the Odroid B. In this case, we are just using 2 modes in the dimensionality reduction, and then you can select the first 2 modes, and note that the PCA is underestimating the results in terms of the simulation, while the kernel, the nonlinear version, can capture very well compared with the simulation. This is just when you reconstruct in terms of the space, and then you can see this is the spatial distribution for the mechanical energy, and then you can see exactly the difference if you use the PCA to reduce the high dimensional or using the kernel PCA. Okay, then now more recently we investigate a complex problem where you have to include the elastic turbulence, and then now we increasing in terms of the viscoelastic model, you can increase in the Weissenberg number, and the Weissenberg number, when you increase the elasticity on the system, you have more chaotic solution or chaotic behavior. Like for example, in this snapshot, you can in this graph you can capture different snapshots and observe the total energy, and then you see that this is more chaotic than just oscillatory one. But in this case, the PCA, it's complex to use the PCA because you need thousands of modes, while now using the idea is to study if you can use a kernel PCA or other nonlinear dimensionality reduction. This is the reason that we try to understand the concept of the autoencoders in terms to including the energy analysis in this architecture or in this pipeline. This is just one idea about the architecture. We have like the input, we input, and then you have the encoder, you create a latent variable space, and then after using the decoder or decoder strategy, you can reconstruct the field, okay? But as we are using turbulence, or as we have many of noise and in this solution because we are using chaotic data, we extend the analysis for these variation autoencoders, and then this is more complex to define, but basically we create on the latent space some information about a probabilistic latent variables. Like for example, we include in this part inside of or before to create the latent space, you include in some information in terms of mean and deviation. Of course, we have a theory behind this construction where you select one distribution, like in this case, a Gaussian distribution, a normal distribution. But the principal part, or the function in this case, the loss function, now we have 2 parts. We have the reconstruction loss, and also one additional term to regularize this function when you are solving problem with more chaotic data. Our idea was using the variation autoencoder, including now some physics information. In this case, basically we reproduce the idea of the energy-based kernel, but now we create one additional term that related to this kernel function. Again, according to the model, if you select the model, the constitutive equation, and then you change this part on the loss, and you include in the final loss exactly like this. And then we preserve the part using the classical variation autoencoder, but we include one additional term related to the energy. And in this case, we want to satisfy the energy according to the viscoelastic model. And we have some preliminary results for this simulation, or for this test. First, observe we have on the left, we using this variation autoencoder energy reconstruction, just using 3 variables to represent the data. We can capture very well if you compare with the simulation in white. While for the kernel PCA, the nonlinear version of the PCA, you included more than 20 modes, but the results are not good, as you can see on this plot on the right side. In summary, we are now trying to improve exactly this strategy to include more physics knowledge or some mathematical knowledge on the loss function to capture using just few modes when you increase in the Weisenberg number and you have a more chaotic simulation. Okay, first part then, or this first slides, I just described the idea behind dimensionality reduction, but now based on physics informed or physics guided strategy. For now, I would like to spend some minutes to talking about reduced order model or reduced manifold representation. The first idea is to construct a simple model to simulate more complex problems. And also we are investigate a different strategy using the super resolution methodology, where you can include an coarse mesh and then try to reconstruct a hybrid version in terms, if you compare with refined coarse or refined mesh simulation. The idea the steps, we have some steps to construct the reduced order model. This is, if you look for the Galerkin projection, is very similar because you just use these steps in terms of reduction, look for the model, and if the model is stable, you can predict or just extrapolate on the time. And finally, we reconstruct in space, like for example, this. I'll talk about one methodology that we decide to use is the sparse identification of nonlinear dynamics. This Cindy is one interesting tool where you can just select the libraries or the candidates for the libraries, and then you represent exactly your dynamics using a more simplified model. Okay, this is a classical, or in terms of data-driven methodology, it's a classical idea. This is just a step-by-step, but I will skip this part in terms of the Cindy. But it's important to say, more recently, we investigate in terms of what type of libraries we should propose with different, for example, with different physics behind the data. In this case, we show that, according to our investigation, irrelevant terms introduce noise and overfitting. And then we propose in this study a more mathematical analysis. And then if you have interest, you can check this work where we clarify the idea of a ranking to select automatically the best candidates according to your data. This was our first tentative using the POD, and then we apply the POD and create nonlinear parametric models using classical ODroidB. Just in this case, we just use ODroidB. And now we are extend this idea for more complex viscoelastic models. And then, for example, observing this case, we have a portrait of the first 2 modes. Using the PCA, we have like this representation. Using the kernel PCA based on the energy, you can capture this representation. And of course, this is more simple to identify than this type of behavior. And then this is the motivation to include more investigation in terms of the kernel PCA energy-based strategy. Using the FINIP, and we included different parameters, but in this case, just to have a basic idea about the difference, we have the kernel PCA for first modes, This is on the top line. While for the PCA, we can't capture correctly using the Cindy prediction. And then this is the Cindy improvement when you use the kernel PCA. I mean, in terms of non-dimensional or non-linear dimensional reduction, combined with Cindy, you can improve the prediction in terms of the modes. And then we are now modifying the values of the parameters, where you can see if you increase the Weisenberg number, you can capture more chaotic situation, and then this is the challenge for numerical computations. All right, this is just one representation in terms of sparse model, or we have two different models. The first one is using PCA, and the second one is using the kernel PCA. Okay, but now looking for the metrics, using the kernel PCA, you can reduce the error for the reconstruction in terms of this plot, the cavity flow. Again, we are using the cavity flow because it's convenient to have some more facility to analyze the error in this simple geometry. This is using the FINIP, but you can extend for other viscoelastic model or constitutive models. Now, one challenge is to extend this idea for elasto-viscoplastic models, where we have the effect of the plasticity, and then you modify the non-Newtonian equation or the non-Newtonian models. But observe that you can reduce error, just change the nonlinear, or just change the methodology to reduce the data. Okay. Now, the second extension is in terms of the energy-based super resolution. This is the pipeline, okay? This is a simple description. You have low resolution simulations, and then you include this data, these snapshots on time. You create the representation in terms of the projection, and using some strategies to predict, in this case, according to our test, LSTM or transformers, you can apply. And after you use a reconstruction phase and obtain a high resolution simulation. This is the pipeline in terms of the illustration. More specifically, we can describe now two encoders and one decoder, because two encoders, because we have part of the training data we are using on the low resolution, and part on the training we are using on the high resolution data. And then we combine these two encoder and create this latent space according to the influence of the different encoders. One important comment is some years ago, according the authors published this paper, and then they used the same idea, but now just for image. Okay, then this is not new. The idea was, you have the loss function, and you separate the parts of the loss function according to your reconstruction. And then you have terms for low resolution to high resolution. You have high resolution and one approximation for high resolution, and etc. But note that in this case, we don't have the physics behind. We have just the information on the data, just the image or something related to the latent space. Therefore, we extend this idea, now including the information of the energy in the last part of the loss function. And of course, we include more term, one additional term, but at least we have the physical control to analyze the influence of the energy error on the loss function. And then we combine this additional term with the traditional one, and we have now a different methodology. Observe the metrics are the same one for neural network or machine learning model studies, and then we just reproduce using these classical metrics. In terms of the training, we have some simulation. In this case, we use just part of the training, like 50 50 simulation while we extend for 12 test case. We change the values for Reynolds and Weissenberg and beta because it's important to create more data in different situations. Okay, results. On the left, we have the classical POD, and we compare with this autoencoder, but modified by elastic, the energy-based term. While here, we included more than 60 or 66 modes, and we compare the methodology. Note that using the autoencoder, we have, after 3 or 4 modes, we can capture with a good accuracy if you compare with the resolution using more than 60 modes, okay? And this is a good way to create this methodology because we can simplify, we can reduce using a small number of modes, and then we can create now using 2 or 4, the reduced order model, using some interpretation to create the models, while for the POD, it's not clear if you try to extend the idea to construct a reduced order model with more than 60 modes. And then this is the advantage to include in the autoencoder and energy-based methodology. Just some results where you can compare. Yes, okay. And then note we have the low resolution, and this is the references on high resolution, and then you can observe using the low resolution, and on here we have the hybrid version. Okay, you combine, this is the output of the methodology, and then you can compare with the high resolution reference and capture the error according to the variation of the time. We capture the dynamics using, in this case, we have the velocity, or the component of the velocity, and one component of the tensor B, or you can reproduce in terms of the conformation tensor. Okay, I think I have a few minutes, okay. But part 2 is related to droplet dynamics, and then now we are studying machine learning models, but to predict the behavior of the droplet dynamics. In this case, the difficulty is to capture the influence of the interface, of the moving interface. And first we analyze a methodology, a multimodal methodology. I will explain some details about this. And the idea is to use this model and then to classify if you have breakup or no breakup in a very specific problem that I will describe on the next slides. It's important, this is not using a large amount of the data. In contrast, we are using a small amount of the data to predict this behavior. And then this is important because we are looking for more efficient method to describe the prediction in terms of the droplet behavior and morphology. In terms of problem, this is the problem that we are using. This is description of the problem. We have different fluids. In this case, we have, like, for example, one with a viscosity, and we reduce the viscosity. And observe in terms of the physics. We have, for a different viscosity, you have a plate and the droplet can cross the plate, and we have a small hole on the plate. And then the droplet you just put there and wait for the behavior of the formation of the droplet or the small droplets in this part. And you capture the breakup after some times of simulation. We are investigating this problem using experimental data and also numerical results. Okay, but in terms of multimodal machine learning, we are using this pipeline or this illustration in terms of the pipeline. We have data, and we have static data where we have the parameters, for example, the fluid parameters and also the flow parameters, the size of the hole, the size of the droplet, the diameter of the droplet. We include the behavior of the energy In this case, we included one additional energy because now we have the surface energy. It's not only the kinematic energy, elastic energy, and now we have the surface energy. And finally, we can use some image for the simulation, and then including these different modality of the data. We have 3 different models. You combine this, and the outcomes or the output is just to analyze if you have a breakup or not, okay? This is the description of the flow, or just the one illustration of the problem where we needed to simulate this physical behavior in terms of the droplet dynamics. This problem is not new. It was first published in terms of Newtonian fluids some decades ago, but now we are using non-Newtonian fluids just to capture the difference in terms of the fluid properties and to combine with the different behavior of the droplet. Okay, the multimodal, our motivation is to eliminate the brute force deep learning that this is very common for image problems. People just using a thousand of data and capture the behavior in terms of classification. In this case, as we have some problem to capture or to construct a robust data set, because you don't have simulation for droplets, like it's hard to capture open data for droplet dynamic simulation. And then our motivation is just using a limited training data, just a very small amount of the training data set, and also reduce time simulation. In terms, we know that this is a time dependent problem, and then we are trying to construct a robust strategy using just part of the simulation, just the beginning of the simulation. And after the beginning, we can continue using the methodology. You simulate part of the simulation, and then you continue using this deep learning methodology. Okay. Of course, we needed to simulate a lot of cases just to test in terms of the accuracy of this methodology. And then we change the parameters, like we change the Reynolds, the Weber number. Now we have the influence of the surface tension. We have the influence of the radius of the droplet and the hole, and also the viscoelastic properties, beta and Weisenberg. For this case, we are just simulating or considering the Odroid B model. And after some tentatives, we have more than 10,000 cases to include in this analysis. The time series property, it's important to mention. In this case, we capture the influence of the variation on different energies, like the kinetic energy, the surface, and the visco dissipation. And then observe, we have time series. And then the idea is to use the time series to help the model to understand or to learn the representation of the morphology, of the droplet morphology. We are using the basilisk as the code to capture this using the axiomatic simulation. On the left, we have the breakup, the formation of small droplets, while on the right, we have just no breakup. We have like the contraction of the droplet due to the elasticity on the model. Okay, it's important to simulate, as I said, part of the simulation we include in terms of a modality, in terms of the image, on the deep learning architecture. And then we use, for example, just 5% of the simulation, we have this type of image, okay? If you increase, like for example, we have like 10%, we have the formation or the part of the formation on this inside the hole. But if you continue to increase the time or just waiting for the final step, you can see the final result here. But again, we are using just part of these first steps. And this is just part of the data modality that we use. And finally, we have this big table with many results, but the importance here is to observe that using just 5% of the training data, you can capture, according to the machine learning metrics, you can capture a good accuracy, and also the F1 score is very good just using part of the training data, just the beginning or just a small part of the training data. And in terms of simulation or time of simulation, the best way to look this is if you increasing the time of the simulation, you can't observe a significant improvement. I mean that in this case, it's possible to use just part of the simulation, the beginning of the simulation, and just part or a very small amount of the training data. The multimodal is the combination of the deep learning strategies like multi-layer perceptron, transformer, and other types of the models that I will skip details, technical details, but basically we combine different modalities to see the difference in terms of the accuracy, and apparently it's the most important thing is to look for the consumption of the time, okay? In terms of the GPU time is we include in here the time used for different combination. Okay, I think, okay, I just included some final comments in terms of multimodality methodology. The idea now is to continue this investigation, but now including more description in terms of the viscoelastic model, just to help us in terms to reduce the simulation using droplet dynamics. Okay, the first part of the talk, it's more about the data-driven methodology using constitutive equation. And the second part is more in terms of the droplet dynamics, and then we are now looking in details this new methodology. Okay, some of my collaborators in these works, we have a recent project now with guys from Rio de Janeiro, Rony Thompson, and also Anselmo. Then Anselmo is in Paris, and he produced a lot of data, and then it's good to training or just to create this architecture, okay, of the multimodal methodology. Okay, thank you so much, and happy birthday, Sheikh Poti. This is a nice talk. Then you have this. Oh, okay, all right, good, all right, okay, great. Thank you.
I already gave a spoiler of this, this photo. Okay, questions? In the first part of your talk about the data-driven of the constitutive equations, do you incorporate the boundary conditions on the loss function? Is that what you do?
No information about boundary condition. In this case, we test, it's independent of the boundary condition. We test for a periodic boundary condition for row, and also for the cavity flow, we have the classical one. But you don't need it to include in this, like physics informed loss function. No, this is just, as we are using a dimensionality reduction, in some sense, this part is embedding on the latent space, independent on the geometry, basically.
But all the tests that you did were for periodic boundary conditions.
And also not, and also for cross lot, you don't have periodic boundary condition. Oh, yeah. But you have inside the square, the little square, you have a type of chaotic flow. And then you can create like some sense dynamics behind this or on this part.
Oh, I see. More questions? Yeah, no, I have a second one. In your droplets, it seems that you are using the Basilisk method,
yes,
to train it. But I mean, isn't the breakup also, because I understand that's a VOF, right?
Yes, a VOF.
So isn't it dependent on the mesh also? So you are incorporating that on the...
Yeah, this is a good question, because now we are working to compare a front tracking, asymmetric front tracking methodology with volume of fluid, Basilisk in our in-house code, okay? And we observe some influence of the methodology and the mesh. All right, then there is sometimes we have like it's not like a big difference, but you can observe the difference according to the methodology. And then now we are including not only Basilisk data, but also in-house front tracking data just to create a different perspective for the algorithm to learn in different scenarios, like this variation in terms of the mesh, the dependence of the mesh.
Okay, I see. Any more questions? No? So let's thank Cássio again. Thank you.
Thank you.
So now we will start the session that we will do our honors to our to our anniversary. And I would like to ask Professor Chamaqui to take the floor, and we'll do a nice presentation about POTI. So it will take some minutes to the setup, right? So just wait a little bit.
I'll try and hold it close this time. Okay. Well, good afternoon. I first came to San Carlos in 1977, I believe, at the invitation of Odila Leti Linares. And the first man I met was Fernão. And of course, we're in the Fernão building. The reason I was asked to come here was actually to supervise some students, in particular, Celia Andrade. And it was Celia Andrade who, in a few years, was the orientador of POTI when he was doing his maestrado. So I think it was Celia who recommended that POTI should come and work with me. I was at Oxford at that time, and POTI and Messias Meninghetti both came along in the same year, and I suggested to Messias that he worked on multi-derivative methods, but I realized that POTI was a very good analyst. So I suggested Cauchy integral equations, quite a difficult topic, but that was my mistake because I wasn't a good enough analyst to help him. So poor old POTI had to write his thesis really on his own, and he did very well, of course. And then he defended his thesis against a difficult man called Ivan Graham, who suggested that there was some error in the thesis. But POTI fought his case, got his PhD. It was a DPhil, of course, in Oxford. And, well, that was the early days. Time has passed, and POTI's become a very famous man now, as we know. So here you are, and here is, I hope, yes, this is POTI at the Royal Society of Edinburgh, signing the book. And this is really how you're inducted in the Royal Society. But there's a much more important thing. You have to drink whiskey. And I was with Potty, so I benefited too. So we have the homenageon. He's a member of the Brazilian Academy of Sciences, of course, the corresponding fellow of the Royal Society of Edinburgh, treasurer of the International Committee for Industrial and Applied Mathematics, and he was president of CIBIMAC, I believe, for 2 terms. So it's quite an, and of course, he was director of this institute, which I failed to mention there. Okay, well, the Royal Society of Edinburgh is, of course, in Scotland, and those of you who don't know Scotland, there's not much to know, really. It's just whiskey, Highland cows, and bagpipes. And here's Potty, the fisherman. Usually you want to catch as big a fish as possible. So Scoopy. Dear. That was it. So I stretched this picture a little bit to make it bigger, but unfortunately it made Potty bigger as well. So this is Potty the caddy. Potty came with me on one occasion when I was playing golf in a Royal Society outing, and that's me swinging the club. And also, he was a good caddy because I actually won the cup, and I was awarded it by Sir Michael Atiyah, whom you may know as he's dead now, but he was probably one of the most famous pure mathematicians in the world. Ayrshire Coast. Potty is a great man for going walks, so we decided to do a walk along the Ayrshire coast. It's a special path. Unfortunately, and I should say this was, I think, in the winter time, some farmer had let his cows out, and the field was extremely muddy. It's about 6 inches of mud, and poor Potty fell on his face, and he was ethnically changed. He was completely black with this mud. And the only place we could find to wash his face was a cow trough, you know, where the cows, the gado, drink the water. But I think the water, because it was winter, was frozen, so I had to break the ice and then pour this cold water over his face. Incidentally, that was a house I built in my retirement. I thought I should do. I would have nothing to do, so I decided to do that. Okay. Now, this was a trip that never took place, but we'd planned to go to Knoydart. Knoydart is an unusual part of Scotland in that there are no roads. You get there by boat, or you can go walking in. And that was what we were intending to do, either take the boat or walk. But somehow we never managed to arrange that trip. Oh, Potty the hot rod. Now, unfortunately, I didn't get a picture of Potty on his motorbike. And this is actually my father in 1938 in a Lagonda. A Lagonda, as you can see, it's a beautiful car. Sadly, he sold it before I saw it. Yes, a tribute to lost friends. I thought we should mention that. Gustavo, looking a lot younger there. I'm looking younger too. And of course, Murillo. Murillo was a very good friend of ours. And there were others too. Valdemir, who we worked with, Potty and I. And there was a young man called Dean, who never actually got further than my straddle. But I'm sure he would have been a very famous chap by now. Okay. These are papers. I'm not going to really say much. Maybe the first one, the underwater scattering, that was a paper actually to do with submarines identifying some enemy. So you had a bending beam equation, biharmonic equation, linked to the wave equation. And if you look at the solution along the bending beam equation, you get a Cauchy integral differential equation. This problem came from David Butler, as you probably remember. And I think David Hanscom helped out a little bit. Anyway, I'm not going to mention these papers, but I will mention some of the collaborators. although these are papers with Potty, there were many other collaborators. And of course, we've got Norberto on the right and Costello on the left. And here's some more Nonato and a young Cassio. That's why I didn't recognize him when he came in. More papers, joint papers. And then this is Ken Walters. So you see, Potty does work with the best people. Ken Walters was probably, he died 2 years ago, he was probably the best rheologist in Europe, and distinguished man. We worked on a dice well problem with him. A lovely man. And of course, his supervisor was Oldroyd, that Jonathan was talking about earlier. Oldroyd B. And yes, Alistair Fitt. He came out for about 5 or 6 days to write a paper. And I was looking at that paper again. It's well over 40 pages, and it's got 100 references. And it's almost a encyclopedia of Cauchy integral equations and where they come from in mechanics, like the Thwaite-Sale equation, flapping flag, and so on. So he became a vice chancellor, Alistair did. He's just recently retired. More papers, and then more authors. There's Macias on the right and Juan on the left. But all joint publications with these guys. So more papers, and then more collaborators. Michael, of course, and Mohanty, Ranjan Mohanty. I was out in India about 7 years ago, and we've continued a little bit of collaboration. More papers. And now to the more recent stuff. This is heart valve. There it is there. This is an older version. And this is David Wheatley. The valve's named after him, the Wheatley valve, the Wheatley heart valve, but it's for an aortic valve. What else? And the man in the middle is Christian Barnard. And he was, if you like, the mentor of David. David was a young physician. I'm not sure he was fully qualified when he was helping Christian Barnard, who of course was the first man to do a heart transplant. David, in fact, was the first man to do a heart transplant in Scotland. But he was also an engineer at heart, and he has designed this valve. I should say that Barnard was quite a ladies' man, and he was, story, I was a school reunion, and Robin Hunter, who was a medic, and he was the president of the Students' Medical Association, and it was round about the time when the first heart valve, the first heart operation had been done, and he asked him across to speak, and he did. He came to Edinburgh, but poor old Robin Hunter couldn't get near him because of all these girls that were very keen on him. Anyway, that's a silly story. Two more collaborators. Of course, you'll recognize Ugo there. And this is Ian looking very severe. Ian Stewart. He's a clever mathematician working on the heart valve. And here is a presidential Ugo talking in the Brazilian parliament. And here's two more people from the bioengineering in Strathclyde. So this is Monica and Chris McCormick. Chris actually was my postdoc about 10 years ago. And that's it. Thank you.
Thank you, Sean, for this nice presentation. And, sorry. Well, now in this tribute session, right? I want just to give Pochi some some small things here. Oh, Cássio, bring this here. Let's share with the world. I saw this picture today. I was amazed by it. Yeah, this is a picture from the graduation, right? Under graduation in 77, right? Is that that? So guess who is who? Yeah, this one is easy. Who is that, Sean? Messias, yeah. and now where is Wally? Oh, where is Pochi? Which one? Anyone? You know, Pochi? This handsome guy here. So a very nice picture. So with this picture in background, I want to invite Pochi here to the floor, please. No? So, Pochi, I want to, in the name of all the people here and our institute and the SEMEAI and etc., I want to deliver you this homage, a small plaque in your honor. If you want to leave like this, yeah, please. It's a great honor for us to have you here, and I hope that you stay around for many years to come, right? Mm-hmm. This is a small gift for you also. I know that you like yeah, I know that you would like that. So, yeah, we have yeah, more or less. Yeah, you can see it. You can see it. Good. Yeah, yes. Please. Discurso.
Fazer discurso? Bom, eu fico muito agradecido, obviamente, dessa homenagem, sei lá como é que vocês chamam, apesar de que não sei se eu mereço tanto. Como vocês sabem, eu nunca fui um grande cientista. Meus maiores dotes são com relação a organizar as coisas, e eu fiz o que pude. Continuo fazendo até os 75. E agradeço muito pela presença de todos. I should speak English. Sean is struggling. Sorry, I forgot that. I'm very happy to have this celebration for my 70 years, and especially for those who came from far away and that work along with the group actually here. And I'm very, very also grateful to the staff of ICMC that helped me with, especially with the big project that we are about to finish in next month. And this project was a very a big challenge, because we in mathematics, we didn't have we were not used to big projects. And this was by far the first one that we had in Brazil. And you see, it's a long-term project. To start with 11 years project, it ended up being 13 years. And I'm very proud that it ended as one of the best projects for FAPESP. And that was told by people in FAPESP, you know, it's not me that is telling. That successful in terms of being a project that fulfilled most of the promises. And our promises were sort of landing in the moon or something when we start with. So that was very important, I guess, for the mathematics, applied mathematics especially, because it was a big number in terms of money, but what was also a project that included people from Unicamp, from Unesp, from ITA, João is here, the group of João in São José dos Campos, and in São Paulo, people in São Paulo. So I think it is, in the end, the result was satisfactory. Well, all I have to say is thank you.
Thank you, Poti. I want to open for the audience who want to speak about Poti. Now's the time. Who want to say something? I will just give the microphone. Who wanna talk a little bit more? Come on, don't be shy. Yeah. Ivani, please.
Eu tenho um mestre, Dr. Celso Charuri, de um movimento filosófico, e as palavras dele hoje cabem muito bem. A medida de um ser é a responsabilidade que esse ser assume. A qualidade e a quantidade dão o peso de uma vida. E você só está integrado ao conhecimento de algo quando você mostra responsabilidade em relação a esse algo. Então, aqui eu tenho um exemplo de responsabilidade. Vocês podem ver pela responsabilidade o peso e o tamanho dele.
Thank you, Ivani. Thank you. Very, very good words. Who else want to speak? Please, don't be shy. You wanna? Leonardo? No. You guys? Nobody? Yeah, perhaps we have some more people. Paulinho, can you put it here? Oh,
Boa tarde, posso falar?
pode falar, Messias.
Olha, é uma felicidade a gente poder participar aí de uma homenagem como essa, viu? A gente sempre fica muito feliz, né? Bom ver amigos aí, né? João, Cássio, Fabrício, Ivani, um abraço a todos, né? Um forte abraço também ao nosso querido Chama Aqui. E a você, Poti, sempre é muito bom ver esse tipo de festividade, sabe? Você merece. Então, eu estou muito feliz aqui de ver você sendo homenageado, né? Então, eu fiz uma pequena cola aqui para a gente não se perder muito. Essa homenagem, Poti, faz jus a uma vida de dedicação, construção de pesquisa, novos conhecimentos, formação de um grande número de colegas, aos quais você impregnou entusiasmo, bom ânimo, né? Em relação ao desenvolvimento da análise numérica, métodos computacionais, matemática industrial. Então, parabéns, meu caro e grande amigo. Parabéns. Para além das suas muitas contribuições, Poti, A nossa pós aqui muito te agradece. Sem você, certamente a coisa seria muito mais difícil. Então, continua assim, meu querido, espalhando a sua maravilhosa e construtiva influência. Você sempre foi e continuará sendo um verdadeiro empreendedor educacional e da pesquisa. Parabéns, um grande abraço. E espero todos aqui em setembro no Cinemac.
Muito obrigado, Messias, por suas palavras. Temos mais pessoas na chamada. Alô? Hello? Olá.
Oi,
Pode falar?
vocês estão me escutando?
Sim.
Oi, mãe, oi, pai. Tudo bem?
Oi, tudo bem?
É para eu falar que você... De você?
Sem cerimônia, claro. Fala o que você achar. Pode ir.
Boa! Bom, eu estou aqui na Itália e eu não podia perder esse momento aqui com meu pai e com minha mãe. Então, queria agradecer meu pai, minha mãe, principalmente minha mãe e meu pai. Os dois acho que fazem parte muito importante da minha vida. E parabenizar o meu pai, né, por ser esse cara que sempre incentivou a gente a ser muito inteligente, estudar e dar o nosso melhor em tudo que a gente faz na vida, né? Então, acho que hoje eu fui em um momento muito importante no Vaticano e aí eu estava olhando as obras e pensando muito nele, porque tinha Pitágoras, tinha Euclides, e eu falei assim, nossa, eu nunca tinha visto a profissão do meu pai dessa forma, né? De uma forma tão importante, assim, né? Tão majestosa. Então, isso só me deu mais orgulho e admiração por ele. E admiro muito ele. Então, parabéns, pai. Te amo muito. E eu não podia perder esse momento, mesmo estando aqui de férias. Mas eu tô muito, muito feliz por você. E tô lembrando de você em cada momento da minha viagem. É isso. Te amo, viu?
Obrigado.
Temos mais um. Pode falar.
Oi, parabéns, pai, tudo bem? Deu sorte que hoje que eu tô de férias também, só hoje, na verdade. Mas eu não tenho discurso, ainda mais improvisado. Então, parabéns. E a Cláudia tá aqui do meu lado. Ela pode falar parabéns também. E é isso.
Oi. Obrigado.
Tchau.
Opa, mais uma.
Oi, oi.
Oiês.
Olá, pode falar.
Entrando para falar parabéns para o senhor Cuminato, né? A cópia aqui dele, não sei se alguém já tinha visto o Cuminato de cabelo, mas aqui está. Então, parabéns, pai. Muito. Estão me ouvindo? Deu uma cortada? Sim?
Sim, tô ouvindo.
Eu não estou ouvindo vocês, mas acho que vocês estão me ouvindo. Então, parabéns, papai. Acho que muito orgulho de você, muito orgulho de toda a sua jornada. Você é uma inspiração para a gente, tenho certeza que para muita gente que está aí também é. Então, fica aqui um abraço e um beijo muito forte para que tenha vida longa, né? Que continue orgulhando a gente, fazendo todas as coisas lindas que você tem feito. Um beijo grandão para você.
Obrigado.
Será que tem mais alguém ou não? Tem, Paulinho? Mais alguém? Não, não, né? Acabaram, né? Tinha mais um, mas acho que não deu tempo. Bom, então, assim, se alguém se encorajou aí, quiser falar alguma coisa, Castelo, você fez assim? Vamos? Ah, Castelo quer falar.
Eu queria dizer que quando eu vim aqui para São Carlos, o Poti estava na minha banca, o Poti, a Neide e o Arenales, né, do concurso de contratação, e foi os primeiros amigos aqui do departamento, e aí a gente pensou o seguinte, vamos criar um grupo? E foi aí que, quando chegou o Murilo, nós falamos, eu, Poti e o Murilo, criamos o grupo de mecânica dos fluidos computacional. E daí teve toda essa construção, esse desenvolvimento do nosso grupo, e deu nisso que está aí. Parabéns, Poti.
Obrigado, Castelo. Mais alguém? Last chance, last call? Norberto, claro. Correto.
Reforçando, né, o que o Castelo falou, também tive essa grande oportunidade, né, de participar aqui, né, de ter a porta aberta e vir aqui, ficar nesse grupo que você criou, né, que o Poti criou, foi realmente uma experiência em todos os sentidos, né, profissional e pessoal. Tá? Então, sou muito grato e parabéns, né, pelo seu grande sucesso. Tá? Parabéns.
Parabéns. Ô, Paulinha, tem alguém na chamada ou não? Não, né? Tá bom. Então...
Vou falar também, gente. Eu cheguei aqui no Instituto em 2008 e o Poti era diretor nessa época, então eu cheguei na gestão dele. E aí tive uma pequena convivência com ele nesse período, tudo, ainda muito meninona chegando aqui no Instituto. E depois, em 2021, eu tive a oportunidade de ir para o CMA e aí, então, começar a atuar mais diretamente. E assim, da parte acadêmica, né, científica, tudo vocês disseram, mas assim, da parte administrativa, o Poti é uma das pessoas que é muito fácil de trabalhar, porque ele está envolvido ali o tempo todo, ele é compromissado, ele é responsável, ele acompanha, ele está sempre atento, ele fez uma gestão maravilhosa do centro, tanto que a gente conseguiu, né, ter uma prorrogação aí, porque foi feito um uso muito consciente de todo o recurso. Ele é a mesma pessoa que ele é conosco, ele é com os pesquisadores, ele é com o reitor, ele é na FAPESP, então ele é muito fiel a ele mesmo, e isso eu admiro muito. Então, obrigada, Poti, por estar com a gente, por confiar na gente, por fazer parte desse projeto, que eu espero que a gente continue com outros, né, por mais um período. Obrigada.
Obrigado, Fernanda. Last call. Eu estou esperando. Mas acho que estou enrolando, mas não tá. Acho que não vai dar tempo, não. Vai, Cássio. Enrola um pouco, Cássio.
Eu acho que vou enrolar aqui. Eu e o Iwan. Não, eu só vou. Assim, eu fui aluno do Poti e só tenho que dizer também, né, como todos já disseram, agradecimento. Mas uma coisa que eu aprendi com o Poti, que eu acho que quem conhece ele sabe, é a questão da humildade que o Poti transmite, aonde ele vai. As pessoas perguntam muito, né? Como ele conquistou tudo isso sendo uma pessoa humilde assim. Outra coisa que ele sempre foi muito direto. Então, quando eu vim fazer mestrado aqui, eu lembro que foi assim aquele choque, porque todo mundo falava, você vai fazer mestrado com Poti? Nossa, você está ferrado. E foi pelo contrário. Assim, eu aprendi muito e eu acho que sigo os passos do Poti em relação a tratar os alunos, que é sendo verdadeiro. Eu acho que a verdade, quando você é verdadeiro, você conquista as pessoas pela verdade, né? Isso, então, é algo que eu aprendi aqui com o mestre e agradeço por todas as oportunidades que o Poti me ajudou, em conhecendo o Chama aqui e outros colegas do exterior, foi por conta do Poti. Obrigado, saúde aí, força para frente.
Obrigado, Cássio. Palmas pro Cássio. Conseguiu. Olha lá. Ei! Alô, Débora? Tá nos ouvindo? Débora? Débora? Hello? Acho que ela não tá ouvindo. Débora? Hello?
Oi.
Pode falar, Débora. Acho que a gente tá ouvindo você.
Tá bom. Eu estou ouvindo vocês bem baixinho, mas agradeço a oportunidade. E eu só rapidinho, não sei se tenho tempo também, só queria agradecer, parabenizar, agradecer quem fez o evento, todos os organizadores, pessoas envolvidas. Agradecer Potir por ter me acolhido, ter passado várias dicas nessa vida, tanto como profissionalmente, academicamente, pessoalmente também. Obrigada pela amizade. E por estar aí junto com a gente trabalhando até agora. Um beijo e sou muito grata pelo carinho e pela amizade. E desejo muitos anos aí de saúde para pescar e curtir essa vida doidada.
Obrigado, Débora. Que bom que deu tempo, porque eu enrolei bastante aqui para dar tempo, viu? Bom, gente, é isso. No more surprises. And, eu queria completar só, vocês viram a abertura desse evento, né? O tamanho do respeito que eu tenho pelo Poti. Então, só queria reafirmar isso, Poti, eu tenho muito respeito por você, muita admiração, e eu tento espelhar assim, minhas ações no que você fez e no que você mostrou aqui ao longo de todos esses anos de convivência, certo? Então, tenha certeza que assim, um pouco do que eu tento ser hoje é muito inspirado pelo que você fez aí durante esses anos todos, tá bom? Então, muito obrigado por ser tudo isso pra gente. Obrigado. Well, now we move to the Best Poster Award, all right? So, Marília, cadê as coisas? Tá aqui. All right. We have our results. And the best poster goes to... No. Eu vou falar... I'm going to speak only the first author, then I say the rest. But the first author is Pedro Bazon. A data-driven modeling of incompressible fluid flow on hydraulic networks was the best paper. Authored by Pedro Bazon, Tiago Queiroz, Francisco Argueta e Roberto Alzas. Vem cá. Para frente. Desculpa, vai. Deixa eu... Obrigado. Ó, pode falar. Ah, sim, ó. Tem um presentinho para você. Você pode.
So just to say some words. So first of all, I would like to thank Professor Alberto Federico Alzas for his support and for all the guidance he provided to me, and also for all the other students, Thiago and Rafa. And well, actually, for those who haven't yet had the opportunity to see the poster, please feel free to get in touch with us. It will be a pleasure to give some details about the work we have been working on, right? So thank you all, especially for those who came to ICMC to celebrate Cuminato's birthday. Thank you, guys.
Well, so this closes this tribute section. I hope that you all enjoyed. And now we'll all go to the coffee break part. Oh, no, first of all, no, don't stand up. Actually, do stand up, but we want to take a picture. So, como é que vai ser, Reinaldo? Todo mundo aqui? So everybody, please come here to this stage, and then we will take a picture, a historic picture.